Hello and welcome to the second video. In this video, we are going to look at the second section of chapter 2, Uniform Accelerated Motion. In this video, I'm going to explain to you how do we get the three equations that we are going to use to solve any problem related to linear motion. Where do we get this equation from? The first equation, v equals to u plus at, is actually the gradient of the graph v against t. So, if we take the dotted line here and place it in the graph so that we can see where the u and the v's and the t. So, yeah, let me just put it there, okay. So, the gradient of the graph, if you remember from our first video on linear motion, I explained to you that the gradient of graph vt is actually the acceleration of the motion. So, the acceleration of the object is equals to the gradient of the line, the gradient of the graph vt. So, at this point here, the value of y is v, and at this point here, the value of y is u. So the acceleration is v minus u divided by, at this point here, our time is t, and at u, our time is 0. So we can just write t minus 0, which is equals to v minus u over t. And then we can rearrange the equation and it gives us at equals to v minus u. So we can rewrite the equation. V equals to, we bring u to the left. So, and then we rearrange so that v is on the left. So v is equals to u plus at. So the gradient of the graph v against t gives us the first equation. Alright, so the first equation is obtained from the gradient of the graph. So this equation is obtained from the gradient of the graph. Alright, so the second equation here, s equals to ut plus half at squared, is obtained from the area under the graph. Let me show. Okay, now I move to a clean slide so that I can write it better. It won't get mixed up with the previous equation that I've derived for you. So the area under the graph vt is actually a trapezium. Area of a trapezium, this area. So area under the graph vt is actually the displacement of the object. Alright, so the area of the trapezium is the displacement of the object, which is equals to half the sum of the length, the sum of the height of the trapezium on each side. So the height from here to here is u, and then plus the height from the axis time to here is v, time with t. Alright, if you remember from our first slide, from the first slide, so we have v equals to u plus at. So this is the first equation, and then from the area under the graph we get s equals to half u plus v times t. So we can substitute v into the equation here. So what we get is half, we bring the t forward, so we get t over 2. So half times t is t over 2, and then u plus v, v is u plus at, and then this gives us t over 2, u plus u is 2u plus at, and then we multiply the half of t into the round bracket. So the 2 will cancel out, so you only left out with ut, and then plus t times t becomes t squared. So you have half a t squared. So basically, you have two equations that you can use to calculate the displacement of the object. Either you are using s equals to half u plus v times t. You can use this equation. You can use s equals to half u plus v times t if you don't have the acceleration of the object. Alright? If you have the acceleration of the object, you can just use this equation instead. Alright, so you have two equations to calculate the displacement of an object, which comes from the area of the trapezium, area under the graph v against t. So how do we get the third equation? Alright, so the third equation comes from, let me open another empty slide. Alright, so we have the equation of, from the gradient of the graph, we have the equation of v minus u divided by t equals to a, or v minus u equals to at. So this is from the gradient. And then we have the equation for the displacement. So from the area under the graph, so we have s equals to half u plus v times t, or we can write it as 2s over t equals to u plus v. So this will be our second equation. So I'm going to correct this. This is not the second equation. So this is the second equation. So if you still remember from your high school math, if you have a plus b times with a minus b, what you're going to get is, you're going to expand this equation. So you have a square minus ab plus ba, and then minus b square. So AB and BA will cancel out. So A plus B multiplied with A minus B will give you A square minus B square. So what we have is U plus V and V minus U. U plus V is also equals to V plus U. Is the same as V plus U. So we can also write this as V plus U. So V plus U, or U plus V, either way. So we have two equations here. So we can multiply the first equation with the second. So if you multiply the first with the second, so I'm going to write the equation again. So you have AT equals to V minus U, and then you have 2S over T equals to V plus U. So if you multiply V minus U, so V minus U, and then you multiply with V plus U, so V minus U is AT, so this is equivalent to this, and then V plus U is 2S over T, so we can cancel out the T, so V minus U times with V plus U, we will end up with V square minus U square, so the T get cancelled out, equals to 2AS, so you will get the final equation, V square equals to, we bring the U to the right, U square plus 2AS. So this is the third equation. Okay, as a summary, coming back to this slide, so from the gradient of the graph V against T, we get this equation here, and then from the area, we have the equation of S equals to half u plus v times t. So when we substitute v into the second equation, we get this equation, alright? And then if we rearrange again the equation, we rearrange the first equation into v minus u equals to at, and the second equation here, this one, I'm going to highlight it. So this equation, we rearrange it into, let me change the color, into v plus u equals to 2s over t. So if we multiply v minus u with v plus u, this will give us the third equation here. So we have three equations, okay, actually four, including this one. Okay, you can also use this equation to solve for uniform accelerated motion. Okay, just for this particular section, you need to be careful with the direction of motion. Either your object is moving to the right or to the left, or the object is accelerating or decelerating. So you need to consider the direction of motion before you substitute the value into the equation. I think that is all for this section. We will do more examples using the module mutual that we have prepared for you. So we'll do the examples how to apply the equation in the module mutual. Thank you very much. That's it for this video.